Hello and welcome back to the second part of chapter 4. So we were talking about cluster analysis and we were looking at this diagram here and we were combining different clusters or groups, if you will. One thing I wanted to point out is that these vertical lines represent a cost of combining groups together with other groups. So the shorter the vertical line, the less costly or dissimilar those groups that you're combining are. So combining, say, look at the size of this line with this group over here is going to be a lot costlier than combining these two groups based on these vertical lines. Another thing that you can do is you can look at and see, okay, where do I have a group of vertical lines that are similar? So I draw this line here and another dotted line here, and you can see I've got vertical lines there. They're all about the same, and I count up how many vertical lines are. And so for this group of clustering, it might be that we have 3 clusters or 3 groups that would be ideal in terms of having the least amount of variation among the groups. Now, whoever's using this diagram could then go back and say, well, you know, if this is a cluster here, all of these right here, maybe I want to break these out because they hold some special purpose or have some kind of special grouping that I want to look at. So it allows somebody to visualize this and see what kind of grouping they might want. But if you're just looking at it to see, okay, what's the preferred number of groups out of this entire set, then you might look at these lines similar to what you have here, and that would say there should be 3. The next thing we want to talk about is k-means clustering. So what this means is you have an algorithm. An algorithm is just a set of computer program steps that randomly assigns your observations to one of the K clusters. So after all your observations have been assigned, then it calculates a centroid or a central measurement of that cluster. So then using those centroid measures, the observations are reassigned to the cluster with the closest centroid, if you will. One rule of thumb you want to look for is that the ratio of between cluster distance to within cluster distance should exceed 1 for any useful clusters you might have. So if we look at an example here, we have 3 clusters or groups, and you can see this circle right there is the centroid. We would assign all the observations to that group. Then we have this green group, and then we have this red group. So this is clustering by observations where you're using age and income. So if you look at this based on what we've got here, then cluster 1 is for relatively younger, low income customers. Right, its centroid is at age around 33 and its income about 20,000. Cluster 2 then is a little older and higher income, and it's about 58, the centroid, and an income of around 47,000. I'm looking at the wrong cluster. 2 is this red one. So that 58 and around 47,000. Then we have cluster 3, and it's even older than the first one, and it has around 53 for an age and a income of around 21,000. So you can get your different groups that way. Next thing we want to look at is the average distances within clusters. And so we can see here the different clusters that we had from the previous chart, the number of observations and the average distance between observations in clusters. So that's a calculation that's been done. And so it says cluster 2 here is between observations is 0.739, so that's a higher number, and so that means it's the most heterogeneous cluster, so that's the most spread out of the groups or observations that are in that. And the closest, the one that has a smaller number, that's the one that's more alike or homogeneous. We can also observe by subtracting these numbers from each other which clusters are more alike and which more clusters are most different. So the biggest difference here would be between clusters 2 and 3, and the smallest difference was between clusters 1 and 2. So some general rules of thumb when you're doing cluster analysis using hierarchical clustering. So it's suitable for small data sets, so usually less than 500 observations, and you want to easily look at the solutions when you have increasing numbers of clusters. And because of the charts that are generated, it's an easy method to observe how the clusters are nested. So k-means clustering then is when you have larger data sets, more than 500 observations. And it's also a good technique when you're trying to summarize the data with k-average observations. So when you're trying to minimize, maybe your amount of data that you have. Also keep in mind that the Euclidean distance is the standard metric for k-means clustering. So it's not very useful or appropriate when you have binary or ordinal data when you can't get an average, because then it's not meaningful. Next thing we want to talk about is association rules. And you can think of these rules as if-then statements, which will give you the likelihood that certain items will happen. So a lot of this might be used in marketing. So if I buy crackers, am I likely to buy cheese, or vice versa? So for those of you in a business major, you're likely to see that in a marketing area. So, and you might hear it as market basket analysis, but it can also be used in other disciplines. Some other terminology you should know about is something called the antecedent. The antecedent is the collection of items or item set that corresponds to the if portion of the rule. So that's what I would call the condition. The consequent, the item set that corresponds to the then portion of the rule. So if that evaluates to true, then the consequent, what are you going to do then? And there's also something called a support count of the item set. And that's the number of transactions in the data that include that item set. So let's say we have a company or a grocery store that would like to get some insight into their customers' purchase patterns, and hopefully from that they can improve the in-aisle product placement and cross-product promotions. So here's what each transaction has. So if we look back at that previous slide, so that's the number of transactions in the data that include the item set. So if we're looking for peanut butter, how many of those transactions included peanut butter? That's what they're referring to. So in this marketing shopping cart observations, an association rule might be if bread, jelly, then peanut butter. So bread and jelly would be our antecedent, and the consequent would be the peanut butter. And what that's saying then is if the transaction includes bread and jelly, then it also includes peanut butter. So that if that's our rule, then the impact of our association rule is sometimes determined or governed by the number of transactions that it may affect. And that's measured by computing that support count. And that means the number of items set consisting of the union of the antecedent and consequent. So for our case, peanut butter and jelly, and then bread and jelly, and then peanut butter. So in the example above, our support count, that is, it has to have bread and jelly and then peanut butter, so all three items, is only 2. We can also measure something called our confidence, which helps us identify reliable association rules. And you can view this as the conditional probability of the consequent item set occurs, given that the antecedent item set occurs. So in our case, again, bread and jelly, and then peanut butter, and versus the antecedent bread and jelly. We would like to see a high confidence here, which means the consequent is frequently true when the antecedent is true. But sometimes this can be misleading. So for example, if the support of the consequent is high, that is, the item set corresponding to the then part is very frequent, then the confidence of the association rule could be high even if there is little or no association between the items. Another thing we calculate is lift ratio, and it's a measure to evaluate the efficiency of the rule. And so it's calculated by looking at the confidence that you calculated up here by the support of the consequent divided by the total number of transactions. So if you have a lift ratio greater than 1, then that it would suggest that it's usefulness to the rule, and it's better at identifying cases or observations than not using any rule at all. So in an example above, if our confidence is 0.5, that is, we've got 2 divided by 4 here, right? Support of antecedent consequence, there's 2 of them. Support of the antecedent 4 is 0.5, and the lift ratio would be 0.5 divided by the result of 4 divided by 10. And so we get a 1.25, which says this is a useful rule. Another way of looking at that then is if we identify customers who purchase both bread and jelly as one who also purchased peanut butter is 25% better. That's the 1.25 than just guessing that a random customer purchased peanut butter. So that's usefulness of this rule. So looking at the example in your book, we've got it broken out as antecedent consequence, support for A, support for C, support for A and C. We calculated the confidence percent, and then from there the lift ratio. So with a 2, it's a good rule, greater than 1, not so good, about the same. Sometimes it happens. It's better than not having a rule at all. And then we see even smaller numbers, which means it's better than not having a rule at all, but how likely is it to occur? And so in evaluating your rules, so ultimately it's judged on how well or useful it can be and how well it explains the relationships between your item sets. So if you look at an example, when Walmart mined its transactional data to find a rule such as if a customer purchases a Barbie doll, then the customer also purchases a candy bar. You know, how reliable do you think that is? You know, it's only good if it's well supported and it helps you explain something that you didn't know before. So it helps you uncover a relationship. All right, so the next thing we're going to cover is text mining. The last thing I want to talk about out of this chapter is called text mining. Text mining also goes by a term called sentiment analysis. So sentiment analysis is trying to get meaning out of a written response back. So your book here uses maybe voice of the customer of Triad Airlines, where they're filling out surveys or responding to something. It could also be as simple as something like movie reviews. It also could be, if you're in the healthcare industry, if you're filling out patient surveys and you want to have some idea of how patients feel about a particular treatment or whatever you've been asking them questions about, you would do some kind of text mining on them. So there's a certain process you go through, and that's what we'll be talking about for this text mining. So because it's text, it's often referred to as unstructured data because it's just letters and you can't put any quantifiable rules to that. So you're going to have to somehow quantify those letters and words. And when we speak of unstructured data, it could also be audio and video, and they're making tools to help you analyze audio and video as well. So something to keep in mind is that because it's text, it's going to be a little bit harder to actually process. So you got to do some pre-processing. So you've got to convert that text into some sort of format that you can then analyze. That is, it's got to become numerical. So the example your book uses is this voice of the customer at Triad Airlines. So they want to find out what is the sentiment of their customers that are using their airline. So they do this by sending out some email and then looking at how people responded. They'll also give them some surveys and look at how they responded on the ratings of certain things, but also to look at the comments that they put on those surveys. So when we talk about text mining, you need to understand that the collection of the different documents that are being analyzed is called the corpus or body, but they're going to call it corpus here. So here we have 10 respondents that have concerns with Triad Airlines. So you see what they all typed in or what they gathered. So this is the corpus. So what does this mean? What's the biggest concern? What's the least likely concern? You would also see this with some kind of social analytics. You know, when people are responding on Facebook or Twitter, they could gather those hashtags and combine that into their corpus for analysis, and you'd have a similar list like you see here. So to be analyzed, the text needs to be converted into some kind of structured data from the unstructured data. So we'll have rows and columns of numerical data. And that will allow us to use the tools that we've discussed about descriptive statistics to be used. We can also map that out with data visualizations, some charts, and then some data mining. So in our case here, our observation or row the first part is going to correspond to the document that it comes from, and then the columns correspond to particular words that we're looking at. So then again, those would be our variables across the top. So you would have then whether a word occurred or not, yes or no, so it becomes a binary term document matrix. So one of the first problems that you'll encounter is well, what are the important words and how many important words are there? Do I make too many, which then makes it difficult to analyze, and you might not get meaningful results from that. The other issue is then if you don't make it big enough, you have too few terms and you might miss a relationship that's in your data. So one thing you can do is look at the frequency of the words that are in your documents, and that will give you some guide as to which words you should be choosing. So in our example, when they looked at this Triad airline data, certain words that showed up a lot were delayed, flight, horrible, recline, rude, seat, and service. So when you convert that into a matrix, you might have, okay, from the first respondent or document, how many times were those certain words mentioned? Or were they mentioned at all? So it doesn't matter how many times it matters whether they're mentioned at all. So again, you need to think about, is it a frequency matrix here you have, or is it going to be just a binary yes or no? 0 is no, 1 is yes. So that's part of the pre-processing of our data. So we're converting that unstructured text into numerical data. And so again, determining what words or terms that you have at the top that you're looking for can greatly impact the analysis. That goes back to, if you don't choose the right words, then you're going to miss the relationships. And so one thing you may hear is something called tokenization. So that is the process of dividing the text into separate terms. And each of those terms then is referred to as tokens. When you get your document, any symbols and punctuations are removed from the document. All the letters should be converted to lowercase so that when you're doing a search for frequency, they all match up. Otherwise, you might have, if you have some that have different cases in them, it won't count them all the same, and you'd have to search for each type of spelling, which you don't want to do. Then you need to think about, okay, words that have the same meaning or the same word but in a different tense, they need to be combined, and they shouldn't probably be considered as distinct terms. So that gets us to something called stemming, and that's converting a word to its stem or root verb, so they all have the similar meaning. Our ultimate goal then of doing this pre-processing is to get a list of relevant terms, and it should be small enough so that it's not too difficult to analyze, and would provide some useful information. So we can use the frequency, can be used to eliminate words from consideration as tokens. So if it doesn't have a lot of frequency, we'll get rid of it. We might combine words that are synonyms that reproduce the set of those tokens again. And there's actually specific software out there that can manually specify terms to include or exclude as tokens. And so I'm going to research some more, but I hope to find a text analysis add-in for a spreadsheet that you might be able to use, and we can actually perform some of these type of calculations. So as you're looking at your documents, you also need to be aware of any slang or humor or sarcasm that can cause problems when you're interpreting that data. And typically, the better software you have, the better it can handle those kind of problems. And then after you've done those sort of things, you want to end up with a set of tokens that you think are relevant for what you're trying to study. If you're having to identify a lot of words, then you want to do that frequency that I mentioned earlier. And what you'll be generating is a frequency term document matrix. So again, the rows represent the documents and the columns represent the tokens. But now the entries in the matrix are the frequency of occurrences of each of those tokens. Remember, the token is that word that you think is relevant to what you're studying and occurs often in those documents. So let's use an example. We've got movie reviews. Right, so we've got some new action film that's been released. You have 10 reviews from critics. You're using your pre-processing techniques. You reduce the number of tokens to only 2, which is great and terrible. And so we'll look at the table that shows the frequency of the term document matrix. That's the next slide. And so from there, we would apply the k-means clustering to the frequency term document matrix to obtain 2 clusters. So here's our text mining. How many times did it occur in each one of those documents? So we want to see if there's any clusters that fall out. So if we're looking at each of these are the variables just like we did before, which ones combine together, and then we can do some analysis, further analysis I should say. Then if we plot those out, we get clusters, one cluster over here. This is the terrible ones, and then these are the great ones that are over here. So looking at this, it seems that cluster 1 is the negative ones, but it seems to be more extreme if it's negative. And then if they like it, it doesn't seem to be as extreme as the negative ones. And so that ends this chapter on descriptive data mining.